So we've talked a lot about partial derivatives, which we love for the applications because they're easy to compute. But partial derivatives, it turns out, aren't very satisfactory from a theoretical standpoint. Partial derivatives don't have a lot of the nice properties that we like for regular derivatives. So let's recall, for example, let's recall proposition 2.2.4. If f is differentiable at x, this is for regular differentiability from the real numbers to the real numbers, then f is also continuous at x. And then, but recall from the homework you just did, there are functions let's say in that previous example, f is a function from R to R. There are functions f from R2 to R that are not continuous. I think in our example, so we had the origin, that's everybody's favorite point, but such that the partial derivatives do exist. We could write f prime is differentiable. Remember, that just means that f prime of x exists. So would like a definition of differentiability that's a little bit stronger, a little bit more rigid than you just have partial derivatives in all the coordinate directions. For example, we'd like differentiability to be strong enough that only continuous functions can be differentiable. We'd like to be able to say that all differentiable functions are continuous. And we're going to be able to define this, but if we want to define a general derivative from Rp to R, or later we'll go from Rp to Rq between two different multidimensional Euclidean spaces, we're going to need to review a lot of linear algebra because we're going to start thinking of derivatives very differently now. So first thing, so I'm going to put up a bunch of definitions. Hopefully most of them will be review for a lot of you, but some of them will be new. So first off, I want to clear up something that you probably saw in high school. So first off, let's let f be a function from the real numbers to the real numbers. And then if f of x equals mx plus b for some constants, okay, you're probably used to calling this a linear function. We're not going to call it a linear function anymore. We want to reserve linear for something else. So we're going to say that this is an affine function. And we're going to reserve linear for the b equals 0 case. So a linear function, 0 always maps to 0. And so the next batch of definitions, basically their point is to tease out what's special about functions f of x equals mx, what's special about the multiplication by a constant functions that make them useful for differentiation. So now let's review some abstract linear algebra. Let's let V be a set. And then we say that V is a vector space and we'll restrict ourselves to vector spaces over the real numbers. You can also define vector spaces over the complex numbers. If you're an algebraist, you can define vector spaces over other stranger fields, but since but in this course, we'll stick to real vector spaces. If there are two operations addition and scalar multiplication, which we usually just write without a symbol, such that for all x, y, and z in our vector space and all numbers alpha, beta in the real numbers, we've got the following conditions. It's a lot of conditions, but they're all going to be pretty straightforward. First off, if you take two vectors in your vector space and you add them together, you're always allowed to do that, and you always have to get something in V. Second thing is that addition is associative. If you add x and y and then you add a z, that's the same as you add y and z together first and then you add x to them. And the third condition is the additive identity condition. I should say it this way, and a distinguished element, a special vector, which is usually just written 0 in V, using the exact same symbol as the 0 symbol for 0 in the real numbers, and we expect you to be able to tell from context which 0 what we mean. But then what's special about 0 is that 0 plus x is equal to x plus 0 for all vectors x in V. Fourth thing we want to assume is that addition is commutative. X plus y equals y plus x. And the fifth thing we want to assume, we're half done, is that for any vector x and y, there is an additive inverse such that x plus negative x gives you our additive identity. And then a little bit of notation. X minus y equals x plus the additive inverse of y. And I'll point out for those of you who have taken algebra that these first 5 conditions, we can summarize them just by saying that V, or rather V under addition, is an abelian group. So a vector space always has to be an abelian group. Under addition, we call the operation addition, the group operation addition. But to be a vector space, you need a bunch of other properties, basically relating to scalar multiplication. So let me remind you what those axioms are. So the first is that if alpha is any real number, we've specified that above, and x is any vector, then you can take alpha times v, that's always defined, and it's always also an element of v. This is much like axiom 1. And we've got that 1 times x is always supposed to be just equal to x for any vector x in v. And I'll point out that there is an equivalent condition here. This condition, and that additive inverse exist, that is equivalent to the condition that 0x equals 0, where the first 0 is the 0 in the real numbers. The second one is the 0 in V. I'll go ahead and put some arrows in this equation to make it a little clearer what it's saying. But you can prove that if every element has an inverse, then 0 times an element equals 0, and if 0 times an element equals 0, then you've got an inverse. It's always minus 1 times x. Once you've got that 1 times x is x, you can show that minus 1 times x must be the inverse. All right, and then the last 3 axioms are talk about how scalar multiplication works. First is that scalar multiplication is associative. Multiply by 2 scalars. It doesn't matter if you multiply the scalars first or multiply them into the vector 1 by 1. And we don't have to write down that scalar multiplication is commutative. We don't have to write down that alpha beta x is the same as beta alpha x, because alpha and beta are real numbers, so we inherit commutativity from the reals. And then we can distribute addition over scalar multiplication, whether we're doing the addition here, whether we're adding 2 scalars, or whether we're adding 2 vectors. So those are the axioms of a vector space. Here are some examples of vector spaces. I think they are all so well known, I will not tell you what addition and multiplication is. But first off, the real numbers are a vector space. They're kind of a silly vector space, but sometimes that's useful, for example, as the base case of an inductive argument. Euclidean space, p-dimensional Euclidean space is also a vector space. And in fact is why we call these things vector spaces. That's the one with all the vectors in it. You can also think of the set of matrices as a vector space. You can add matrices, you can multiply them by scalars. Sometimes we write this as R2 times 2 to be the 2 by 2 matrices. Here's another example that you may recall from ODE if you've taken Math 2584 or at this university or undergraduate ODE for engineers at most universities. There are a bunch of properties that can be summed up at, say, the set of all functions y from the real numbers to the real numbers that are as solutions to your favorite differential equation, for example. Your favorite homogeneous linear differential equation. That's a vector space. That is in fact a two-dimensional vector space, and an awful lot of Math 2584 is exploring the consequence of this fact without ever actually saying this is a two-dimensional vector space. There are some infinite dimensional vector spaces. These are vector spaces where the vectors are in fact functions. So you can take the Riemann integrable functions on an interval, the continuous functions on an interval, the C7 functions. That is the functions where they're continuous and so is their first derivative and their second derivative, and so on up to their seventh derivative, or even these smooth functions. These are the functions that have derivatives of all orders. These are all vector spaces. Next definition, hopefully this is a general linear algebra definition that you've seen, is of a normed vector space. V is a normed vector space. If there is a function which we usually write with triple bars, but it is just a function from V to the real numbers, such that we need two things to be true. If we let the distance from x to y be the norm of x minus y. So if D is defined in that way, then D is a metric. So VD is a metric space. And that means you've got your usual metric space axioms. So the norm of x is 0 if and only if x is your 0 vector, and you've also got the triangle inequality, which you can write like this. And I'm not writing down the symmetry axiom for normed vector spaces because it follows from the next little property. And that's on top of being a metric, you've also got to have this property. Alpha times x is the absolute value of alpha times the norm of x. This has to be true for all scalars alpha and vectors x. So we can put norms on some of our example vector spaces above. Real numbers with the absolute value let's write this as norm of x equals absolute value of x. You can have RP with the norm of x being our favorite Euclidean norm. You can put several other norms on this. They are all norms as we've seen. They all turn RP into a metric space, as we saw in section 5.81. And they also have this additional homogeneity property that you can move scalars out. And if you want to treat, say, the continuous functions as a vector space, you can make that a normed vector space by taking the supremum of not f, but its absolute value. Or you can also use the Riemann integral as your norm. So there are lots of normed vector spaces. In chapter 6, we're mostly going to be looking at Euclidean space with RP with the Euclidean norm. That's this one with the squares and the square roots in it. But I want you to be aware that there do exist other vector spaces, just like there do exist other metric spaces. Now let's tease apart what's so special about linear functions, why we like linear functions better than affine functions, and let's see if we can state it in a little bit more generality. Let's let V and W be vector spaces. And a function L from V to W is linear if we have the following two conditions. The first is that L of x plus y is L of x plus L of y for all x, y in V. And the second is that you can move constants out. You can move scalars out. L of alpha x equals alpha L of x for all vectors x and scalars alpha. So a couple of examples of these guys. So if L of x equals a constant times x, then L is linear. Where m is some scalar. And conversely, if L is a linear function from the real numbers to the real numbers, then L of x is x times L of 1. So if we let m be L of 1, so L of x. So multiplying by a scalar is always a linear function, and these are the only linear functions on from the real numbers to the real numbers. But there are much more exotic linear functions. For example, if L of f is f prime, L is the differential operator, then L acting from, say, the 3 times differentiable functions on the interval from 0 to 7, going to the only twice differentiable functions, that is linear. So differentiation is linear, the Laplace transform is linear. There are all kinds of linear operators out there. 2 more definitions and then we'll be done with this storm of linear algebra definitions. We will not be done with linear algebra. So a linear functional so not a function, a functional, we add an AL to the end on a vector space V. That is a fancy name for a linear function whose range is the real numbers. So it's a function from V to the real numbers that is linear. So, for example, if V is R3, then L of x1, x2, x3 equals 5x1 minus 2x2 plus 7x3. That is a linear functional. It's a linear function whose range is the real numbers. And another example, if V is, let's say, the Riemann integrable functions on some interval, then L1 f of f, then L of f equals the integral from a to b of f. That is a linear functional. And if V is the continuous functions, let's specify from 0 to 7, then you can check that L of f equals f of 3 is a linear functional. Its domain is the real numbers, since all your functions have range is real numbers, and you can check that L of f plus g is f of 3 plus g of 3. L of alpha times f is alpha times f of 3, that it behaves over addition and scalar multiplication the way you think it should. So we have a special notation for all the linear functionals. As you might guess, these are super important in linear algebra. If V is a vector space, then V star, that's the set of all linear functionals on V. And then if V is a normed vector space, and L is in V star, L is a linear functional on V, we let the norm of L, that is the supremum of all L of x as long as you're not dividing by 0. And notice that V star is a vector space. The dual of a vector space is a vector space under pointwise addition and pointwise scalar multiplication. That means that L plus M, if L and M are both linear functionals, then L plus M is also a linear functional. It's L plus M of x is equal to L of x plus M of x. And then the linear functional, if alpha is a scalar and L is a linear functional, alpha L is also a linear functional. Alpha L of x is equal to alpha L of x. So now let's talk a little bit more about linear functionals on RP, on Euclidean space. So let's start off with the following proposition. Let's let L be a linear functional on RP. And then remember we saw that the only linear functionals on the real numbers are multiplying by a constant. Well, it's going to be very similar. The only linear functionals on Euclidean space, on a finite dimensional vector space, is inner product with a constant. Then L of x. Here's what it has to be. L of x is, you take xj, remember, where x is x1, x2, up through xp. So xj's are the coordinates of x, and the ej's are the coordinate vectors, the vector with a 1 in the jth position and a 0 everywhere else. And I'll point out we can always write x as the sum from j equals 1 to p xj times ej. The ej gives you a 1 in the jth place, and multiplying by xj gives you an xj in the jth place. And if you're familiar with your inner product notation, you can write this as the inner product of A with X, where AJ is L of EJ. And the proof is pretty quick. It follows from that marginal note I've got over there. L of X, that's L of sum from j equals 1 to p xj times ej. And then because it's linear, you can break it up over the sums. straightforward induction argument, you can break it up over the sums from 1 to p. And then because the xj's are scalars, you can pull them all out. So that's easy enough to write. And an exercise, a homework or exam study problem, is that if L going from RP to R is linear, then L of x, it's the inner product of A with x for exactly 1A. There is exactly one A in RP such that L of x is the inner product of A with x for all x in RP. The proposition we just proved shows that there is an A. It's the L of the EJs, and the exercise is to prove that that's the only A that will work. And we can work out what the norms of these linear functionals are in terms of this A. So let's let V be RP, and we'll say that the norm on V is our standard Euclidean norm. Absolute value, or you can just square it if it's a real numbers. Let's let L be a linear functional on V. And A is as in our previous proposition. Then the norm of L is equal to the norm of A. And I want to emphasize this is special about this norm. We'll see a couple of examples after this. So here's how we prove this. So first off, by the Cauchy-Schwarz inequality, if x and A are in RP, which they are, then L of x, we remember that's the inner product of x with A. Sum from J equals 1 to P xj aj. Let's write out what the Cauchy-Schwarz inequality says. This is less than or equal to, okay, I've got to take a square root, but that's okay. And then if we write out, if we work out what that is, that's the norm of x. Well, norm of x squared times the norm of A squared, but then you take the square root to get rid of them. So if x is not equal to 0, so the norm of x is not equal to 0, then L of x over the norm of x. It's less than or equal to the norm of a. So we have that norm of a is greater than or equal to the supremum of those L of x over the norm of x's. And we remember this is exactly how we defined the norm of L. So now conversely, if A is not equal to 0, then we've got that the norm of A, that's the inner product of A with itself, is the norm of A squared, so let's divide by the norm of A. But that's L of A over the norm of A. Everything's positive. This is absolute value of L of A over the norm of A. That's one of the things we take the supremum of to get L, so we can put A less than or equal to the norm of L. And then on the other hand, if A equals 0, then L of x, and our product of x with 0 is 0 for all x. So that thing we take the supremum of, all of them are 0, so the norm of L is 0, also known as the norm of A. I want to emphasize that this is special to our favorite metric, our favorite norm on Euclidean space. So, for example, let's let V be RP. And let's suppose instead of our Cauchy-Schwarz square norm, we take this, the sum norm. Where you take the sum of the coordinates instead of squaring them and adding them and then taking the square root. Then if L is a linear functional on V, well, proposition 6.2.8 still works. So there, you can still write L as the inner product with some A. Then in this case, the norm of L is not the norm of A anymore. It's not the sum of the absolute value of A. It is, in fact, the maximum of the AJs. Not the sum of the absolute value, the maximum of the absolute value. And I think I'll leave that as a homework or exam problem, but it is something I may ask you to prove at some point. Last thing I want to say before we get back to derivatives, let's let V be a normed vector space. And L be a linear functional on V. If the norm of L, which we defined a while ago, is finite, and notice that this is always true, if V is RP and the norm of X is our standard Euclidean thing, then so a linear functional whose norm is finite, L is uniformly continuous. It is continuous. It's better than that. It's uniformly continuous. It's better than uniformly continuous. It is Lipschitz. On V. And then how do we prove this? So if X, Y are in V and X is not equal to Y, then the distance in all, remember, distance in the real numbers is the absolute value. So L of X minus L of Y, absolute value, that's the distance from L of X to L of Y. And then because L is linear, we can move the X minus Y inside. And then because X is not equal to Y, this norm, the norm of Y minus X is not 0, so I can multiply by it and divide by it. And then our norm of Y minus X just hangs out front for a moment. Our second piece, notice that's the quotient in the definition of norm of L. So norm of L is the supremum of things that look like this. So we can put norm of L. And then when we're trying to write this as a Lipschitz function, as a metric space, we remember that the metric in a vector space, the distance from X to Y, is always the norm of Y minus X. And then if X equals Y, then the distance from L of X to L of Y, well, that's just 0, is equal to the distance from X to Y times, we can throw in the norm of L. We're multiplying by 0, it doesn't matter. And so then, so L is Lipschitz. And we recall from section 5.4 that a Lipschitz function is always continuous, is always even better uniformly continuous.